Here we are given three vectors v1, v2, v3, and we are told to apply the Gram-Schmidt process to find an orthonormal basis. And also, in the process of it, do a QR decomposition of this matrix, which is made of these three vectors as column vectors. As you can see, 1, 4, 8 is this 1, 4, 8, and so on and so. Now, Gram-Schmidt process has to do with two things. One is to make vectors as unit vectors by dividing it by its size. That's called normalizing. And also subtracting the component of previous vectors so that the new vector will be perpendicular to the previous vectors. So let's start and see what that means. V1 is obviously not a unit vector, so let's calculate the norm of it, which is square root of 1 squared plus 4 squared plus 8 squared, which is 64 plus 16, which is 80, 81. So you get 81, which is 9. And therefore, U1 is the normalization of V1, meaning that you divide it by its size, and that's 148 divided by 9. Now, for the purpose of calculation, it's easier to use this in the future, but when you write down the orthonormal basis, you should write it like this, because you're trying to write one vector. This is a vector with a scalar multiplication, whereas this is just a vector. Let's move on to calculate U2. U2 is obtained by starting from V2, subtract the component of V2 that's in the U1 direction, and you want to multiply U1 here so that this is a vector and then vector minus vector. And this, if you can easily check that this resulting vector will be perpendicular to U1 just by doing a quick calculation with U1. But it won't be a unit vector, so you still have to normalize it by dividing it by its size. Okay, so let's just calculate the numerator first. V2 is 322 minus 322 inner product with 148 over 9, and then 148 over 9. You want to pull the 9 in front, and then let's do the inner product, which is pairwise multiplication and add, right? 3 times 1 is 3, 2 times 4 is 8, 2 times 4 is 16, times 1/9 of 148, and you also want to record the following for the future reference, that U2 is equal to V2 minus, what is this value? This is 11 plus 16, which is 27. 27 divided by 9 is 3, so you have 3 times U1, right, over some value, which will be the norm that we have to calculate. Okay, so this is 3, and then 1/9 of 3 is 1/3, so it will be, let's see, let's make everything as 1/3 times something. So 3 is 1/3 times 9, 2 is 1/3 times 6, and 6. And then this entire thing is 1/3, so you have 148 subtracted, so minus 1, minus 4, minus 8, and that's going to give us 8, 2, 2, negative 2. Okay, we need the norm of that. And when you do a norm, and if you have a constant multiple, then you can just take the constant multiple outside as long as it's positive. If it's negative, you just have to take the absolute value and bring it outside. So we're going to take the norm of what we just computed, but after taking the 1/3 outside, we have the norm of this thing, which is square root of 64 plus 4 plus 4, and that's going to be 72. And because 72 is 9 times 8, and 9 can come out as 3, so you end up with square root of 8, which is equal to just 2 radical 2. Okay? And then you want to put this 2 radical 2 under here. Okay. So if you're just doing a question where you use Gram-Schmidt to find O and B, you don't have to write this, but we will need this for the future. Okay, let's carry on. We're not done yet. U2 is now this numerator divided by this, so it will be 1/3, 8 to negative 2, then 2 square root of 2, and then as you can see, everything here are divisible by 2, so if I cancel the 2's, it'll be 4, 1, negative 1, and then you'll get 1/3 square root of 2 times 4, 1, negative 1. Again, when you write the final answer, you should really put this inside, but right now this will be the preferred form to calculate U3. Okay, so we got this so far. U1 as 148 over 9, U2 as 4, 1, negative 1/3 radical 2. U3 will now be, take away from the V3 the components in the direction of U1 minus the component in the direction of U2, so that this resulting vector will be perpendicular to both U1 and U2. And then you divide it by its size. Okay, so let's carry on with the numerator first. We could just continue with this, but that takes too long, so we'll just calculate the numerator separately. V3 is 3, 1, negative 5 minus 3, 1, negative 5, inner product with 148 over 9, and then 148 over 9, and then minus 3, 1, negative 5 of 4, 1, negative 1 over 3 radical 2, and then 4, 1, negative 1, 3 radical 2, and that's going to be, pull out the 9 in front, and then 3 times 1, which is 3, 1 times 4, which is 4, negative 5 times 8, which is negative 40, and then 1/9 of 148, and then minus, again pull the 3 radical 2 in front. 3 times 4 is 12, 1 times 1 is 1, negative 5 times negative 1 is plus 5, and then you have 4, 1, negative 1, 3 radical 2. Again, for the purpose of QR, you want to write that when we do U3, we had to take from V3 minus, what was this number? This is 7 minus 40, so that's going to be negative 33. Oh, but because it's a minus and minus, it'll be plus positive 33 over 9, but they are reducible by dividing by 3, so you have 11 over 3 times U1. This much is U1, right? And then minus let's see, this is 13 plus 5, that's 18. 18 divided by 3 is 6, so you have minus 6 over square root of 2 times this one, which is u2, divided by its size, and we'll have to figure out the size later. Okay, let's move on. So we have so far figured out that you have 3, 1, negative 5, and then 3 got reduced. This was negative 11, so it's plus 11 over 3, but there's another 9, so it's 11 over 27, 148. And then this one is, well, square root of 2 times square root of 2 gives you 2, but then 18 is divisible by 9, divisible by 2 and 9. So 3 times radical 2 times 3 times radical 2 happens to be exactly 18, matching with this, so that they cancel out completely, and you just have 4, 1, negative 1 subtracted. Okay, since these two don't have any denominators, let's just compute these first. So we get 3 minus 4, which is negative 1, 1 minus 1, which is 0, negative 5 minus negative 1, which is negative 5, plus 1, which is negative 4. And then we have, when we have 11 multiplied, it's 1 over 27 of 11, 44, 88. And furthermore, if you make everything over 1 over 27, this becomes negative 27 plus 11, which is negative 16, 0 plus 44, comma 44, and then 27 times 4 is 108, so negative 108 plus 88 gives you negative 20. And we see that these are all divisible by 4, so let's pull the 4 out as well. It helps us when we take the norm. So it's negative 4, and then 11, and negative 5. Okay, we still need to figure out the norm of the denominator, so let's calculate the norm of the denominator. Norm of the numerator. Norm of the numerator. It's going to be 4 over 27. Pull that outside when you calculate the norm. It's negative 4 squared, which is 16. 11 squared, which is 121. Negative 5 squared is positive 25. So 25 plus 16 is 41. 120, 162. Okay, so we have 4 over 27, square root of 162. Okay, so now we can put everything together. The numerator is 4 over 27, negative 4, 11, negative 5. The denominator is 4 over 27, square root of 162. 4 over 27, 4 over 27 will cancel. And then, by the way, since we found this value, we should put that in here. 4 over 27, square root of 162. Okay, and then this, you can see that 162 is twice of 81, so and 81 is square root of 81 is 9, so you can make the denominator as 9 square root of 2, and then you can write this as negative 4, negative 5. Okay, so that's our final vector, and we actually found the orthonormal basis. These three vectors will be an orthonormal basis, but then what's left is to do the QR. Okay, now the answer for the orthonormal basis, and then I also copied the previous relations that u1 is v1 over 9, and so on and so on. And by the way, let's simplify this a little bit, because I know that this is 9 radical 2. 9 and 27 can cancel, and so this can be 4 over 3 radical 2. That looks easier. Okay. All right. So now we have to figure out the QR decomposition, and the way you do it is by taking all of these and solving it for V1, V2, and V3. So the first one says V1 is equal to 9 times U1. The second one says, well, you first have to multiply 2 radical 2 and then add the 3U1. So that gives you plus 3U1 plus 2 radical 2 U2. And then V3 is you multiply this to the other side, and then you have and then you also have to move these to the other side as well. So it's negative 11 over 3 U1 plus 6 over square root of 2 U2, and then plus 4 over 3 radical 2 U3. Now it's up to you to do rationalizing the denominator. If you do the rationalizing of the denominator by multiplying radical 2 top and bottom, this actually becomes this becomes 2, so that this becomes 3 times radical 2. So actually, let's do that. Let's rewrite this one as 3 radical 2. And then now all you have to do is put this into matrix form. And if you write V1, V2, V3 as the column vectors, you have 1, 4, 8, 3, 2, 2, 3, 1, negative 5. And on the right side, you can rewrite this as a Q matrix, which is U1, U2, U3. So that matrix is going to be these. So write down 1/9. Actually, let's see, 9. Right. So you have 1/9 and then 4/9 and 8/9 as the first column, and then U2 is 4 over 3 radical 2, 1 over 3 radical 2, negative 1 over 3 radical 2, and then U3 is negative 4 over 9 radical 2, 11 over 9 radical 2, and then negative 5 over 9 radical 2. That's your Q matrix, because this is a orthonormal basis. Orthonormal basis will make up orthogonal matrix. And then times you have an upper triangular matrix. See, 9, 0, 0. When this is multiplied like that, then 9 will only get multiplied to the first U1, and it's going to create the first column of the multiplication, which would be equal to 148. And then the next one is 3 and 2 radical 2. So you have 3 and then 2 radical 2 and then 0. Then if you do the matrix multiplication, you'll see that 3 will be multiplied to the first column and 2 radical 2 will be multiplied to the second column. And then finally you have negative 11 over 3, 3 radical 2, and 4 over 3 radical 2. And again, that's going to be exactly translating this one. So now what you have is a QR decomposition of this given matrix. QR decomposition means you have a orthogonal matrix times an upper triangular matrix.